And here we go into question 3. So, later in the hockey match, Nicole takes a penalty corner. She hits the stationary ball toward her teammates. So we've got to state Newton's third law, which refers to forces during the collision between the ball and Nicole's stick. The second part, we're looking at hitting with a stick velocity of 18, stick continues forward, calculate the velocity of the ball. To me, this is a collision, so conservation of momentum is being asked about. And part C, let's see, part C, the ball of mass blah 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 is shot towards the goal but hits the goalkeeper's leg guards instead, has an initial velocity of 30, time of impact 0.2. To me this looks like, we've got asked about the average force of the impact, so this is momentum and impulse. And then part D again looks to be an impulse question. It's about force and time. So classic impulse question. Right, so let's go back and actually look at how we answered these. 3A, for every force, so Newton's law is that for every force there is an equal and opposite reaction force. Now I'd like to relate this, I think, to the stick and the ball. So the ball and the stick experience forces of exactly the same magnitude but opposite directions. Alright, so what about part B? Now let's think about the data we've been given, so we can make it very clear to ourselves what we're doing while we work on this. So the stick velocity is given as 18 meters per second before hitting the ball, and 12 meters per second after hitting the ball. So let's write that: Vs 18 to the right, and then 12 to the right. The velocity of the ball. Quite clearly it's a stationary ball when hitting the stationary ball, so the initial velocity is 0, and we've been asked to find out what it is afterwards. What about masses? So the mass of the stick is given as 600 grams. Again, we need to convert that to SI units, so 0.600 kilograms, and the mass of the ball is 160 grams, which we convert to 0.160 kilograms. Alright, now the assumptions. Now the critical assumption here when you're ever doing conservation of momentum is that there are no external forces acting during the collision. If we want to really relate this well to the question, we need to think, where could they come from? And it would be Nicole. If she swings the stick and then is still putting force in during the collision, then we would expect that perhaps there's actually some of the acceleration of the stick going on and stick and ball for that matter, going on as the collision occurs. So we have to make an assumption that that is not happening, and that it's all due to the momentum of the stick when she hits the ball. So in that case, then the momentum before would equal the momentum after. Now momentum equals mass times velocity. That's P equals mv. So the momentum before is the mass of the stick times the velocity of the stick, which gives 10.8 kilogram meters per second. The momentum after, P after, equals the momentum of the stick plus the momentum of the ball. Now the momentum of the stick is 12 times 0.6, and the momentum of the ball is 0.16 times whatever the velocity of the ball is. And between them they have to equal the momentum before, which is 10.8. So we put that together, and we get that at 7.2, that's the momentum of the ball, the momentum of the stick after, plus 0.16 times the velocity of the ball equals 10.8. We rearrange by subtracting 7.2 from both sides and then dividing both sides by 0.16. And we then solve and get that velocity of the ball equals 22.5 meters per second, which is 23 meters per second to two significant figures. Given that we were given the speeds of the stick and to only two significant figures, that seems appropriate. Alright, what about part C? Now, the change in momentum equals the force times the time. This is the impulse equation. And this really comes directly, when it comes down to it, this comes directly from Newton's second law. So the change in momentum equals the momentum after minus the initial momentum. So the final momentum minus initial. Now in this case, the tricks in that are, well, there aren't really too many tricks in this, except to note that the ball has rebounded, so the momentum after is a negative number compared to the momentum before. So the actual change in momentum is not 30 minus 10, it's minus 10 minus 30, or minus 40. Sorry, that's the change in velocity, is minus 10 minus 30, not which gives you negative 40 as the change in velocity, rather than negative 20. And the time is given, and so you can now work out that the change in momentum equals force times time, so force equals the change in momentum divided by time, and ultimately gives you a force of 320 newtons to two significant figures. Right, the fourth part of this question, and the last part of the exam, is asking for a more qualitative answer, and it's got this this idea here that if the change in momentum equals the force times time, that means that the change in momentum is the area under this graph. So the first thing we are asked to do is add a second graph to the diagram to show the effect that leg guards would have on the graph shape. Now, overall, the momentum of the ball must be approximately the same, or the change in momentum of the ball must be approximately the same, irrespective of whether it hits the person on their unguarded shin or on their shin with leg guards. That means that the area under the graph, which is representative of the change in momentum, must be about the same in the new graph we're going to draw. The second thing is that what we expect to do is that the collision will take longer. So I've started by thinking about a point further out along the axis where the collision ends, and then I'm going to create a curve that's got about the same area under it and extends to about this further point. So it's got a lower peak to it, and it's kind of more spread out. Alright, so now to explain this. So first, thick pads will absorb energy, but that's not really what they want you to be talking about. They want you to be talking about momentum. So what I'm going to talk about is that the absorbing the energy means that the collision will be less elastic. And when I'm thinking absorbing energy, a spring absorbs energy in a very elastic way. So perhaps my words absorb energy isn't the right thing. Perhaps we'll dissipate energy would be better. Dissipate energy, meaning that the collision will be less elastic, meaning the ball will not rebound as fast, and the change in momentum will be lower, and this would reduce the area of the force versus time graph. So what I'm suggesting there is that it's not actually the same, it's actually going to be slightly less. Secondly, the pads will increase the time duration of the collision. And I think this is what they're probably gunning for, because this is a very standard answer in NCEA exams. So this reduced change in momentum will be spread over a longer time. This will reduce the average force of the impact and the peak force of the impact. Now, we have to also explain how this benefits the goalkeeper. This will protect the keeper by reducing the force of the impact. And possibly, particularly the first idea that the ball will rebound less, would have the effect of allowing them to snaffle the ball or get hold of the ball because it won't rebound away from them quite so fast. I'm not sure that was asked for. Maybe I've gone a little further than even the examiner was thinking in this. And there we go. So that is the final answer to the final part of the final question of the 2019 exam. Thank you for watching.